Okay, so let's get started. Oh. Okay, is it better now? It's not better now. Let's see. Is it better now? Okay. Okay, so this is where we left off. We talked about throttling a little bit. I didn't give you the ideas. But I decided we don't really have enough time to go into heterogeneous multi-core, so we're going to stay in networks for a little bit longer, if people are okay with that. Otherwise, I was going to move to heterogeneous multi-core, but we cannot do justice to it in the time remaining, unless I speak really fast. Okay, so I'm going to go back to this work, because I think it's really good to push the boundaries. I'm going to talk about this minimally buffered deflection routing a little bit more. Is that okay with people? So we're going to go into a little bit more depth, because I think there's actually a lot more to do in this area between buffering and not buffering. So we were talking about bufferless deflection routing. That's good. And the downside that we're trying to target in this work is at high network load, the deflection routing causes unnecessary link and router traversals. It reduces network throughput and application performance and increases dynamic power. So the goal is to improve high load performance of low-cost deflection networks by reducing the deflection rate. So we're going to take a look at that, basically. You already know the background, so I'm going to skip through this really quickly. We already covered this, right? Basically, we solved the correctness issues which led to performance problems with the chipper. But there is also a performance left on the table, which is how do you avoid performance degradation at high load? And this has really been the Achilles heel of bufferless networks. And I think the solution that we're going to talk about is really MinBD, which is minimally buffered deflection routing. So there are key performance issues. One is link contention. There is no buffers to hold traffic. Any link contention causes a deflection. Ejection bottleneck, I mentioned earlier. Only one flit can eject per router per cycle. Simultaneous arrival causes deflection. So you've done all this work to get the flit out there, and now you're going to deflect it back for some time. Not a good idea. And the last one is deflection arbitration. If you build a permutation network like we've discussed, like you've noticed, sometimes deflection arbiters deflect unnecessarily, right? Because they don't have the full permutation. They have a partial permutation, and that actually makes the router simple, and that makes the router approximate, but that increases your deflection rate. So how do you actually reduce this? Yes?
Injection bottleneck, they're actually two very different, fundamentally different situations. One is the temporary contention.
Yeah. Mm-hmm.
The other is the truly, two are trying to send large stuff to the cell.
Exactly. Mm-hmm.
Then it won't help you naturally unless you throttle,
Yeah.
causing deflection.
Yeah. But if you have dual ejection, then it handles two of them, right? You're always ejecting dually.
Yeah.
That's right, yes. That's right. But ejection, as I will show, ejection can be earlier or later. You don't need to actually complicate the crossbar in ejection. We'll talk about that. I think that's the realization. Basically, these are the solutions. Basically, we want to use side buffers. We want to eject up to 2 flits per cycle. And we want to have a new priority scheme silver flit to handle these 3 different things. And I think you can do other things also. This is just to give you ideas. So let's take a look at the link contention part. So any link contention causes a deflection. Buffering a flit can avoid deflection on contention, but input buffers are expensive, right? You don't want input buffers. All flits are buffered on every hop. High dynamic energy. This is really an overkill, basically. Large buffers are necessary if you actually do input buffering. So this is high static energy and large area. Basically, the key idea is add a small buffer to a bufferless deflection router to buffer only flits that would have been deflected. You know which flit is going to be deflected. Don't deflect it. Buffer it in a side buffer. That's the idea. So this is the baseline router. This is the injection and ejection ports that happened earlier than this permutation network. So these are 2 flits that need to go to those destinations. The red one gets deflected for whatever reason. The blue one gets to its destination. So the idea is this, basically. You have a side buffer that feeds back into the router. You can call this a loopback buffer also. The thing that's supposed to get deflected doesn't get deflected. In the next cycle, basically it gets from the side buffer. Yeah. Sorry. Yeah, the one that's, let me go back. The same scenario as before. Now we have a side buffer. This one is supposed to get deflected. This one gets its destination. But this last one doesn't get deflected, but it goes into the side buffer. So the idea is to remove up to 1 deflected flit per cycle from the outputs. You could, of course, increase the number of 1 here with additional complexity additional buffering. And this goes back over here. Now you prevented one deflection, and you re-inject into it when a slot is available, and hopefully you go to your destination. And you prevented one deflection. Basically, you handled the deflection locally as opposed to causing trouble to somebody else down the network. That's the idea. Okay, and this is actually very powerful, I think, and we'll see the effect on the deflection rate.
So you wait until you can.
You wait until you can inject, exactly. Yeah, if there's a lot of congestion, you wait for a while. Then basically, it has all the benefits of buffering, except you don't do it all the time. So this could be very small. Okay, so relatively, bufferless routers, deflection rate reduces. Basically, this is what we do. We said that already. So for Flit buffer, reduces deflection rate by 39%. And we looked at different Flit buffers. And relative to buffered routers, buffer is much more efficiently used. You don't need to buffer all Flits. You get basically similar performance with the 25% of the buffer space. So ejection bottleneck, I've already given you the idea. Flits deflect unnecessarily because only one Flit can eject per router per cycle. It turns out in 20% of all ejections, greater than or equal to 2 Flits would have ejected. But all but one must deflect and try again. These are empirical numbers. And clearly, these deflected Flits cause additional contention.
You deflect only once. If it goes from the buffer,
But it can come.
priority. Or it can, you can get sort of, how do you call it, tornado?
Yeah, you could get those, right?
Okay.
You could deflect once, and then it happens to be unlucky it gets deflected. Then now it goes far away from the destination for a while, right? So you could get tornadoes, or you could also get really far away deflections. Yeah. Yeah. So basically, if you do this, you can reduce the deflection rate by 21%. And that's the other idea. You reduce deflections due to single Flit ejection port by allowing 2 Flits to eject per cycle. So how do you do that? This is single with ejection. One of them ejects, the other one, if you have a side buffer, it goes into the side buffer in this case. Okay, basically, and then later it comes and it gets ejected. Now we're going to do this. That's the idea. Okay, but it doesn't help the baseline routers that much. So we basically add this to the baseline routers and look at the performance, but don't add the power area cost, but it doesn't add the baseline routers that much. Yes?
Side buffer is actually just with one slot and can only give you a second chance in the next time slot. And then you get deflected for
Oh, I see.
router because I think it resembles, it's not identical to the various techniques of the power of choice among two.
Yeah, yeah.
Now give you 2 candidate slots.
Yeah.
The immediate and the next. And because the other traffic coming in is unrelated,
Yeah, exactly.
it's like flipping a coin twice. Your probability of failure to get your way is P. Probability of failing twice is P squared.
Yeah.
P squared is
Yeah.
variable.
So basically a single slot buffer as opposed to 4 Flit.
Single slot and even either you go or you get deflected. You can't even spend there more than one.
Yeah. The problem is, once you take things out of the buffer, you need to have a way of going through this permutation network again, right? And the only way, the easiest way we could put it is basically injecting again into the router. I think if you want to get rid of it quickly, you need to have some separate path somehow. We didn't look at that path. Right. I think that's the downside. Once you take it out, putting back in is not hard. It's not easy if things are flowing into the router. But I understand what you mean. So we looked at one Flit router, which buys you something. So 4 Flit buffers is good, but we don't immediately take it out. We take it out when you can. Okay. Okay. The last one is improving deflection arbitration. This is basically the silver Flit idea. Sometimes deflections occur unnecessarily because we use very simple priority schemes, like golden Flit, for example. You could use full priority order. That gives fewer deflections, but that requires slow arbiters. So if you have golden Flit and two-stage permutation network, you prioritize one packet globally and arbitrate other Flits randomly. But that random common case leads to uncoordinated arbitration. So if you remember golden packet, golden Flit, this is what happens, right? We discussed that already. Each block makes a decision independently, but if you actually have a lack of coordination, you can cause unnecessary deflections, as some of you realized earlier. Basically, all flits have equal priority. Let's assume that there is no flit is golden, which is the common case in the network. You have pseudo-random arbitration. Red flit wins at the first stage, so it tries to go to the red destination. Blue flit goes that way. And green flit loses at the first stage because of randomness. It must be deflected now. Right. So basically, you get an unnecessary deflection. Yeah. So red flit actually loses at the second stage. You get an unnecessary deflection over here. So actually, both of these deflections are unnecessary, as you can see, right? Because you're putting random choices. So if you want to improve this, add another priority level. And you want to actually add maybe more than one priority level. But if you actually do add one more priority level, you gain a lot of benefit because you ensure that at least one flit is not deflected in each cycle. So highest priority is one golden packet in the network. It's chosen in static round. I don't know what's happening. Maybe. Okay. Is that better? Okay. Basically, the highest priority is this. One golden packet in the network. It's chosen in static round-robin schedule, as we discussed. This is really static round-robin schedule, and it ensures correctness. The next highest priority is one silver flit per router per cycle. Basically, it's chosen pseudo-randomly and local to one router. And the goal is to enhance performance. So basically, if you add a silver flit, at the beginning, you randomly pick one and say, red flit is the silver. No flit is golden. Red flit is silver. So I'm not doing it. It's obvious right now. Okay. So basically, no flit is golden, but red flit is silver. Red flit wins at the first stage because it is higher priority. And then green flit is deflected for whatever reason. And then red flit wins in the second stage. At least one flit is not deflected in this case, as you can see, right? You could actually improve this by adding one more priority level, or you could actually make each of these blocks a little bit more complicated by picking over here. But then that increases the complexity also. Yes?
Why don't we simply mark the packet that lost in the first stage? Because you know it's already being deflected.
Yeah.
And then in the second stage, if you have a loser versus winner,
You pick the winner, basically. Yeah, exactly. I think. Yeah, exactly. I think you can actually. That's a very good idea. I like that idea actually. Basically, you can improve this even further. So there's a lot of interesting tricks you can play over here. Okay, so basically, this side buffer solves the link or reduces the link contention problem. This dual port ejection reduces the ejection bottleneck problem. And being a little bit more intelligent about how you handle the prioritization inside this permutation network reduces the unnecessary deflections. So where are we after this point? That's the idea of min-BD. So this is a very similar infrastructure, but hopefully better examples. We're going to look at a bunch of buffered networks. And we're going to look at chipper. We're going to look at some other bufferless buffered hybrid router that was proposed by someone else. Basically, the idea is you have coarse-grained mode switching. You switch between bufferless and buffered modes over here to try to get the best of both worlds. But you pay the cost of buffers. In this case, you have to have buffers. And these are some common parameters that we have. Router latencies. We still look at 2D mesh. And we assume dual ejection for baseline routers for performance reasons. And we modeled everything again in Verilog and power and area. So these are the deflection rates, basically. This is baseline, and these are three different components of the min-BD router. And min-BD router is the combination of all of those components. This is side buffer, dual ejection, silver flits, and side buffer plus dual ejection, and the min-BD. And this is the baseline. What is the baseline? That's a good question. Okay. Baseline is chipper, I think. Say it again? So these are averaged across many workloads. Yeah. Basically, all mechanisms individually. So baseline is, I believe, either bless or chipper, but it's not said here. I believe it's chipper. All mechanisms individually reduce deflections. As you can see, it should be chipper. Your deflection rate reduces over here. And then here, as you can see, the deflection rate reduces individually. But then side buffer alone is not sufficient for performance because you have the ejection bottleneck actually. So you need to actually combine all of the techniques. So as you can see, this is the overall. Overall, you get 5.8% over the baseline, 2.7% over dual ejection, and you reduce the deflection significantly. And actually, if you employ your idea, for example, you would reduce it even more. But we didn't really over-optimize this. So the key takeaway is you get better performance. And you can read the paper for more detail on the performance analysis for everything else. Okay, so this is another interesting case. Basically, this is, again, real applications, but we classify them based on the injection rate they have into the network. And this clearly shows that if your injection rates are high, your performance is lower. That's true for buffered networks also, by the way. It's not true just for chipper, AFC, and MinBD. But as you look over here, these are the bufferless networks. This is average across all workloads. These are the bufferless networks, the three of them. As you reduce the size of buffering, your performance goes down. Chipper is closest to the network that has the lowest amount of buffering. This is bufferless buffered hybrid, and this is MinBD. So MinBD gets you better than the small amount of buffering and close to large amounts of buffering. So basically, you're better than chipper. At high load, you're much better than chipper, as you can see over here. And you kind of close the gap between buffered and bufferless. So that's the idea, as expected, right? And now we're much better. Before, the performance loss was much higher. Now we're getting closer to buffered. Okay, and so the performance is actually similar to, slightly better than the lowest amount of buffering over here in the buffered router. But we use 25% of the buffering space only. Okay, so these are the overall power results. They're very similar to before. As you reduce the size of your buffering, power consumption reduces. This is chipper. This is bufferless buffered hybrid. Basically, switch between bufferless routing and buffered routing, but you need to have buffers to be able to do that. That's why this is relatively high over here. And this is MinBD over here. And these are the different breakdown of the power. So most of the power here is spent, well, a good chunk is spent over buffers here. As you go this way, there's little power in the buffers. We add a little bit more power in the buffers to actually reduce overall power, as you can see over there. Okay, there should be a line over here. Okay, and these are dynamic versus static. As you can see, dynamic power increases with deflection routing over here. But overall, you save power because you reduce the buffers significantly. Okay, the blue part is the dynamic power. So we can actually reduce the dynamic power by reducing the deflections. Okay, I don't know why this is going back. Okay, this is the slide I wanted, actually. This has a mind of its own also. So you can look, this is actually the most reliable result so far that we've obtained other than in meshes. So if you look over here, we did also a performance power spectrum exploration. These are different buffered networks in terms of the network power. Clearly, as you increase the buffering, your network power increases. And this is performance. And you would really like to be somewhere over here, right? Well, somewhere over here. You would like to push that way. And I believe this is MinBD, or one of the examples of MinBD, yes. And MinBD also has a spectrum, but it's not plotted over here because it has the side buffer. You can vary the size of the side buffer. So according to our results, this is the most energy efficient of any evaluated network router design so far. Okay, I'm going through this quickly, but hopefully this is obvious. So we looked at die area and critical path as well. This is your normalized die area. And MinBD is very similar to chipper, slightly higher because of the buffering. And you still reduce area significantly compared to a mid-sized buffered network. Okay, and this is the critical path. So our critical path is higher than chipper, unfortunately, because we add a little bit more. It's about 7% over chipper because we have the buffering and we have the ejection, dual width ejection, right? And also the silver flit. Don't forget, all of these actually add a little bit to your critical path. But it's not terrible. So hopefully still within your cycle time. Oh, okay. So that gets us to the conclusions of this. We've already discussed this. I've already shown you the slide, so I'm not going to go over this. So this is the state of the art, at least in mesh type of networks, in terms of deflection routing. Yes?
One thing I think you just didn't mention is in mesh specifically, along much of the path, you really don't care among two options. If I need to go northeast, I say I need east, but really I couldn't care less if you push me north.
Yeah.
It's not a deflection, it doesn't cost anything.
That's right.
So there are deflections that don't cost
Yeah, so those are not deflections, actually. I simplified the graph over here.
We actually allow,
Exactly. There are two productive ports you can have, usually. Not always, but usually you have two productive ports.
take that into account.
Yeah, it's taken into account. Yes, exactly. I just want to simplify the graphs for sure. Okay. Okay, so let's switch gears a little bit, talk about packet scheduling a little bit more. We're going to forget about bufferless for now. Does that sound good? Okay. So I think there are a lot of issues here also. I'm going to give you some ideas. Let's see where this takes us. So which packet to choose for a given output port? That's the key question over here. And we've been talking about it. And router needs to prioritize between competing flits. So which input port do you pick? Which virtual channel do you pick? Or which applications packet do you pick? And we're going to talk about this applications packet a little bit. So there are common strategies that are used in buffered routers. As I said, you use round robin across virtual channels, or oldest packet first, or an approximation of it, or prioritize some virtual channels over others. And none of them are actually nice, because none of these actually take into account the application behavior. So we wanted to use application characteristics. You're on chip, you know that the packets are coming from some applications. Why not use them? Why be application oblivious? So this is going to be very similar to what we've done with memory scheduling earlier. But I wanted to talk about this because it's important, because every resource needs to be a little bit more application aware in a system where you can be. Okay, so we're going to talk about this. So this is starting again, but I'm not going to move. So basically, you have a bunch of these different applications, and you're injecting stuff into the network on chip. Does it make sense for your network on chip to be application unaware? And the answer is no. So we've already seen this. I'm going to skip this. This router is going to make decisions, basically. So conceptually, let's assume that you have a very contented router, and these are color coding different applications. Let's say you have 8 different applications, and in the router, you need to make a decision. Router is essentially a scheduler. Which application does it pick? Or which packet does it choose? So existing scheduling policies at the time were round robin or age-based. Actually, many of them were round robin. Basically, you go through the virtual channels round robin. If there's an empty one, you pick the thing to schedule from there. Very simple, very small critical path for the router. It doesn't take into account age, so that's great. The problem is, if you have such local policies, they're essentially local to a router, which means that these can lead to contradictory decision-making between routers. So packets from one application may be prioritized at one router to be delayed at the next. So you have no coordination across the routers. As a result, it takes a long time for a packet to move from source to destination, because it waits here, it gets prioritized here, it waits here, it waits. So it waits most of the time, basically, until its round robin priority comes in. So this is terrible from an application perspective if you think about it. And the second problem is it's application oblivious. So this also is a problem of application obliviousness, maybe. But the second problem is explicitly application oblivious means that you're treating all application packets equally somehow. And we know already that this is not a good idea, right? There are some applications that would benefit from getting their request serviced very quickly from the network or the memory scheduler. And there are some applications that do not really care because they have so many packets to begin with that they're not going to be delayed much. As a result, because the applications are heterogeneous, we want to have policies that are application aware. And we want to have policies that are a little bit more coordinated globally, as opposed to making only local decisions that are really myopic, that really do not help you in the bigger scheme of things. Okay, so let me give you an example of the scheduling. This may remind you of memory scheduling also, but it's very similar actually, except for the coordination component that you have across the routers. If you look at a router internally, it's actually a simpler problem than memory scheduling, if you think about it. Memory scheduling needs to consider banks, buses, channels, ranks, robo for locality, parallelism, but this doesn't need to consider any of that. So let's assume that this is the packet injection order at the processor, these different cores. This is injected first. Yeah, it should have a number 1. This is second cycle, third cycle, fourth cycle, ... And these are different cores. And we're going to have a batching policy over here. I'm going to not talk about that over here, but basically, you're going to timestamp things based on batches. This is your batch, and this is your other batch, and this is your other batch. And we're going to rank these applications again. So it's going to be very similar to memory scheduling. It's principles of parallelism or batch scheduling without the parallelism awareness really applied to a router. Basically, we're ranking some applications higher than others. Why? Because this application has the possibility to make the fastest progress in its core. It's not injecting as much. This application is injecting a little bit more. This application is injecting a lot. So it makes sense based on what we've discussed so far to rank this one higher somehow, because it's going to make its core, if you service this, the core is going to make progress very quickly. So that's our ranking order. You somehow compute a ranking, and the router does that ranking and obeys that ranking in its scheduling. So let's take a look at different scheduling policies over here. I'm not going to give you exactly how the router does it, but you can read the paper for more detail. So this is round robin. If you do round robin scheduling, this is really application unaware. And let's assume that you go round robin from the top to the bottom. You first take that one, that one, that one, that one, from different virtual channels. And this is your time. The first one that gets serviced is this one. So if you look at the stall cycles with round robin, they're pretty high. This poor applications packet gets scheduled after 8 time units. This one after 6. This one after 11. So your average is 8.3. If you do age-based means whenever it's injected, you have a timestamp, and based on that timestamp, you actually order things. So what is age-based? You basically, this has a timestamp 1, so it gets scheduled first. This has a timestamp 2. This also has 2. This also has 2. And this is how you schedule things. Now, if you do that, that's a bit better, but the average is still pretty high. You get 4, 6, 11. So it only helps the green application. Now, if you schedule based on intensity, what you do is you form a ranking based on the intensity of the applications. How do you do that? Well, in this case, we assume some global coordination. Basically, over time, you figure out which applications are how intense. And there's a global coordinator that says, OK, this should be your ranking. And you obey that ranking for some time. And if you do that, and you can do that on a chip relatively easily, I think. Basically, if you do that, all routers obey that ranking. And this is what will happen in a given router. So in a given router, you basically reduce the stall time for these 2 applications. You don't affect this application that much, but your average stall time or average latency actually reduces. And the other benefit is because all routers obey the same ranking, now what happens is you don't make decisions in a router that contradict a previous router. All routers prioritize this, the packets that are coming from this non-intensive application. That way, that packet flows through the network quickly, goes out. The packets from this application flow through the network next in the sense that they get the second level of priority. And this application gets the last pick, if you will, in the router. But it doesn't get delayed that much because it's very intensive to begin with. Yes? Yeah, basically it's shortest job first scheduling. I'm not sure if you were here when we discussed the memory scheduling. That's how I motivated the parallelism or batch scheduling with shortest job first. That helps in this case also. But I think you're gaining from 2 things. One is you're in a coordinated manner prioritizing a given application in the same rank across different routers. That helps a lot actually because you don't make contradictory decisions. I think existing routers, I actually don't understand how they work really well because it's very inefficient, right? It's like, it's essentially like you're at a traffic light over here. You have to stop. And the next traffic light you go. When the next many traffic lights, you have to stop, right? Somebody else is prioritized over you. So you make very slow progress. And I think a lot of people know how annoying it is to drive in a traffic light like this, right? You'd rather flow through traffic lights and everything becomes green. And you get prioritized. That's essentially what's happening with this mechanism for applications that do not inject much into the network. OK. OK, and that's the paper. If you're interested, you can take a look at it. So later, we've actually looked at other things. So this is actually a good mechanism, but it turns out you can do much better. It turns out you have a lot of slack. If you're injecting a lot of packets into the network, and all those packets need to go and then come back, but some packets take longer, which means that those longest packets are the ones that determine your slack. Every other packet can be delayed by the amount so that they all get serviced at the last moment, right? That's the idea. You have, because of your multiple packets, you have some slack in some of your packets, and you can use that slack to prioritize other applications. And this actually impacts performance a lot. And if you have some other measure of slack for whatever reason, you can actually take advantage of that. So this slack-based scheduling actually improves performance even more than what I just discussed earlier. But I'm not going to talk about that. So we looked at a bunch of other quality of service schemes as well. There are a lot of ideas over here, which I'm not really going to get into. I may actually talk about this one first. Yeah, I'll talk about that, because I think there are some interesting ideas over here. Any questions so far? OK, so let's talk about this topology where quality of service. Wow, this is a mind of its own, maybe. So basically, the motivation is clear. And we want, this actually tries to solve many things at the same time. It's an overall system design, but I'm going to focus on a couple of ideas only. So we want high efficiency, area, energy, good performance, and strong service guarantees. I'm going to focus on the last one. And the key idea of the strong service guarantees is we want to be topology aware in terms of quality of service. The problem is if you have quality of service support in each router, it's actually expensive. We talked about memory scheduling, right? It's expensive to have quality of service or fairness support, and we try to reduce the complexity. Now, if you think about network routers, and you have 1,000 cores, and if you have, I don't know, 1,000 routers, that's a lot of overhead in your router. And we actually tried to add quality of service support. If you're really interested in that, you can take a look at that paper. This tries to actually reduce the overhead of quality of service support in routers, but it still has a lot of overhead. So our goal was to provide quality of service guarantees at low area and power cost in this case. And the idea is, if you really want quality of service, isolate some of your shared resources in a region of the network and support QoS within that area only. Maybe all of your memory controllers are over there. All of your shared caches are over there. And ensure that you design the topology such that applications can access the region without interference. That's the idea. And pictorially, this is what happens today. Today, you may have, ignore some of these numbers over here. You may have virtual machines that are mapped over here, for example, another virtual machine that's mapped over here. And these virtual machines may be partitioned across the network. So as a result, you actually have quality of service in all of the routers in your network. And these may be your shared resources, an example over here. And I don't know why the color doesn't match. maybe for some people it matches, but for me it doesn't match over here. OK. So basically, you have quality of service everywhere. As a result, this is expensive. And as you can see, the virtual machine is partitioned over here. So to get the shared resources, you need quality of service somehow. OK. Basically, you have a contention inside the shared resources for memory access. Intra-virtual machine traffic, you have shared cache access. That leads to contention. And you have inter-virtual machine traffic, where you may have page sharing across virtual machines, and that leads to contention. So when this virtual machine is trying to access this shared resource, let's say memory controller, this other one may also be trying to access that shared resource, and they're going through these routers, and you need some quality of service. They contend with each other. OK, so we want actually network-wide guarantees without network-wide quality of service support, because these routers are expensive. So the key insight over here is we want to leverage rich network connectivity. You want to naturally reduce interference among flows through the topology and limit the extent of hardware quality of service support. This requires a low diameter topology. Basically, you want to reach from here to here in the network very quickly, right? In a single hop, ideally. That's the low diameter part. And we're actually using multi-drop express channels. If we have time, maybe I'll talk about that also. But that's one way of having a small network topology. Basically, it's a multi-drop bus. That's the idea. As opposed to having, you go from this place to this place, and you have a router in between. And then you go from that place to that place. You have another router, another router. Have a single link, single bus, and have multiple drops out of it to access different resources. OK, basically, it looks like this. You have a single bus, and you have multiple drops so that you can go inside whatever resource that you're trying to access over here. So it's called multi-drop express channel. It's an express channel because you can go directly over here and then drop over here. You don't need to go through a router. Well, you have a router, little routing logic to decide whether you go here and here and here, basically. So we're going to make use of that. But you can actually use something else that provides you that kind of connectivity, as long as you can go through multiple hops without stopping between the hops. OK, so basically, the first idea is we have these shared resources that are dedicated, and there's quality of service inside them. If you want to go from here to here, you have a quality of service aware router, for example. Rest of the die is quality of service free. But we have a richly connected topology to provide traffic isolation. So basically, that's the idea over here. If for this virtual machine to reach this quality of service aware region, you can directly go through there. For this virtual machine, same. You can directly go through there. For this virtual machine, you can also directly go through there. So basically, you have direct connectivity to your quality of service regions. Okay, and this is not allowed in this case, basically. We disallow some communication because we cannot support quality of service for this communication. So you have to go through these quality of service aware regions. So if you want to communicate from this portion of your VM to this portion of your VM, well, too bad. You cannot go through this. You need to go through that way. That's the idea. It's a very different idea than the design mindset so far, which says you should put quality of service everywhere. Okay, let's see. Basically, the advantage is you limit the quality of service complexity to a fraction of the die over here. And you have optimized flow control. Basically, you reduce the buffer requirements in the quality of service free regions. There's not much buffering over here because you don't support quality of service. So it's actually good. And the paper actually discusses a bunch of other things to optimize the energy efficiency inside here. But we're not going to talk about that. That's why it's called KiloNoc, actually. It's how do you actually design a much more scalable and efficient energy efficient topology, plus buffering, plus flow control in a system that looks like this. Okay, this is the evaluation methodology. You can read the paper. There are a bunch of names over here, as you can see. So we compare to the baseline that looks like this. You have quality of service at each node. And you have quality of service only in shared regions. And you have more optimized flow control. And this is the proposed organization. I'll just give you the high-level results. Basically, if you have quality of service in all of your network, this is the area that you would get for a given number of nodes, 1,024. It's a lot, basically. And most of it is in the routers, as you can see. Links are a small fraction of the time because the small fraction of the area, but your routers are big because they actually need to support quality of service. And you can ignore these, but basically, with the design philosophy that I discussed and the approach that I discussed, you can actually reduce reduce the area significantly, as you can see. Okay, I think you can read the paper for more detail. And there are different kinds of routers, obviously, over here. These support quality of service, and some of them don't support quality of service. And as you can see, going from here to here and here, we actually optimize this routers that do not support quality of service quite a bit. I'm trying to shared regions, basically. Yeah, these are the shared region routers. We should have called them quality of service routers, actually. So once you support quality of service in some, they consume something. But now you can optimize the other routers significantly because you don't need to have stringent guarantees. And the paper goes into a lot of detail. You can take a look at that. Okay, so this is the energy comparison also. These are intermediate steps, as I said. This is the final thing. This is energy, and you reduce energy significantly because most of your routers don't need to support quality of service in this case. Okay, and if you're really interested in the load latency curves, these are the load latency curves that you get. Okay, I've covered this very quickly because we don't have a lot of time left. But basically, it's a heterogeneous network on chip architecture for large-scale networks. And one of the issues with large-scale networks is you don't want to support quality of service everywhere. As a result, you introduce heterogeneity in terms of quality of service. You limit the quality of service support to a fraction of the die. And you leverage low-diameter topologies, MEX, multi-drop express channels being one of them in this case, to get to that quality of service region. And you can improve NOC area and efficiency and provide strong guarantees. I didn't talk about that, but this actually is in the paper. If you're isolated to reach the quality of service region, actually, you get a very strong guarantee to begin with. And this is the paper that discusses the ideas. Okay. When are we supposed to end today? Oh, is it 12:30? Okay. I thought it was a whole day after 12. Okay. So let me very quickly give this, and then I'd like to leave room for questions because There's no other topic that we can cover in more detail. Maybe I'll go through this really quickly, maybe not spend too much time on it because it's a different topic right now. But I like this topic also. This is another area of topology design. And then we'll take questions, and then we'll talk about the exam. So basically, we wanted to, when we were looking at this, we wanted to look at different topologies also. As you can see, this is a relatively old paper today. And I'm not going to cover all of the concepts. I'm going to give you the basic idea. So if you look at two-dimensional mesh, everybody was doing two-dimensional mesh. There are pros and cons over here. You have low design and layout complex, simple and fast routers. The problem is large diameter. Large diameter means you basically, that's the maximum distance within the network, right? It's a lot over here. And you get an energy and latency impact. So we wanted to look at lower diameter, more express topologies, if you will. So concentration is an idea that was proposed. I don't know what happened here, but I think you can see most of it. Let me see if any other pros or cons are hiding. Okay. Basically, the pros over here is you concentrate. You have some sort of network inside here. It could be a bus. And you concentrate that, and you have a single router controlling that multiple nodes. And it could be applied to many, many networks, right? It doesn't have to be just mesh. Basically, multiple terminals are attached to a router node. You get fast nearest neighbor communication via a crossbar. In this case, internally, it's a crossbar, but it could be a bus also. And you get top reduction proportional to the concentration degree. The degree of concentration is 4 in this case. You concentrate 4 nodes in a given square. The downside is your benefits are limited by crossbar complexity. But it opens up a big space, actually, design space. I just want to make sure this is, I don't know why this happened. It's a copy-paste error. Okay. Is this better? Yeah. Okay. Okay. Yeah, basically, benefits are limited by crossbar complexity. So concentration is in general a good idea, actually, whenever you can do that. The side effects are you get fewer channels, and you have greater channel width. Because you concentrate, actually. As you can see, as opposed to connecting 1 to 1, you're connecting 4 to 4, right? So if you keep your bandwidth constant, you're getting 4x bandwidth in each channel. Okay, so replication is another thing. You basically replicate the channels as opposed to concentrating them. You concentrate internally, but you have 2 channels over here. You get bisection channel count. As opposed to keeping bisection bandwidth constant and making channels wider, you actually partition the channels, right? Or replicate, in this case. You restore the channel width, you reduce the crossbar complexity. You can think about that. This is basically, you can think of it, this is concentrated mesh. This is concentrated mesh times 2 with lower channel bandwidth, but you have multiple channels. So this is a topology that was proposed in 2007. It's a basically butterfly topology that we discussed earlier, but it's flattened to fit on chip networks. And the goal was to improve connectivity and exploit the rich wiring budget. So if you look over here, the network looks like this. From each concentrated place, you have one link over here. Basically, horizontally, you have connections from one place to every other one, horizontally. That's the idea. Now your channel width reduces, assuming you're keeping the bandwidth constant between the concentrated regions, but you have many, many more channels. So you have more flexibility. If you're going from here to here, you hop onto this one. If you're going from here to here, you hop onto this one. And now you have an express channel going from there to there. And you do it vertically also. And once you do all of the connections, this is the mess you would get. It's flattened butterfly. Yeah, I mean, this has some layout issues, of course. Yeah, we're going to have something that's better to lay out, in my opinion. But it's going to lose some of the benefits of this also. So the pros of this is it's excellent connectivity, as you can see. You get low diameter. It's 2 hops. If you want to go from here to here, you hop onto this express channel from here to here. And then from here to here, you hop onto this express channel. That's 2. And cons is you get high channel count. If you do the calculation, you get k²/2 per row and column, because everything is connected to every other, right? And you get low channel utilization, because if you're communicating between here and here only, you cannot use the other connections, right? That's the downside of partitioning in general. And this is a partitioned channel network. And you get increased arbitration complexity because your diameter is because your radix is actually higher, right? As you can see, you get 3 connections out here and 3 more connections this way.
How well you can
Route?
scale this?
Yeah, you can.
You can,
You keep adding them.
no, you need to have more
Yeah, exactly. I think that's one of the downsides of the scalability. Yes. Okay, so this is the idea in this work. We want to have similar connectivity somehow, but we want to have more scalable channel count, as you said, and better channel utilization. And the idea is, why not have multi-drop express channels? As opposed to having separate links to each of them, have a single link, but have a multi-drop bus. And multi-drop bus is something that looks like this. You can drop at any drop point. And that's the idea. And you can do it over this way as well. Well, you should do it over that way if you want to be symmetric. And this is the thing that you would get. It still looks a little bit more complex compared to the baseline. So there, it's not as easy, but it's easier than flight and butterfly. And we're going to compare to that. OK. So basically, this is what your router looks like. But I'm not going to go through that since we don't have a whole lot of time. So this is a one-to-many topology. You go from one to many possible places. It's low diameter still. You get 1 hop and 2 hops at most. Now, as opposed to having a lot of channels, you have k channels per row and column, right? And pros is asymmetric, but a con is also asymmetric. So this could be a pro or con, right? Depending on how you take advantage of that. And you get increased control and arbitration complexity because of this multi-drop nature. So basically, you need control complexity over here and arbitration complexity. But it's not a full router with a huge radix, as you can see. OK, so basically, this is actually, this is a spectrum of things. This is MEX. We're going to have some fun with it. It's a multi-drop bus. You can partition it. You have 2 multi-drop buses with half the link bandwidth. So you could actually have 2 separate things, as you can see. Flat and butterfly is actually something like this, right? Except it's not multi-drop. It actually has different links to go to different things in the same row, different concentrated regions. Well, I guess this is partitioned compared to this one, but it's really replicated compared to a single baseline. And if you look over here, this is the partition MEX. So you can get actually closer to flat and butterfly a little bit. Basically, you have this, and you don't connect all of the buses, the same bus to all of the nodes, but maybe every other node, right? If you do that, now you're maybe kind of starting to look like this. So there's a continuum of these topologies, and the paper actually talks about that continuum of these what we call express cube topologies, or generalized express cubes. That's interesting. So there's a huge design space that I'm really not going to cover at this point. But these are some examples of concentrated mesh, flat and butterfly, and multi-drop express channels. So if you look at the radix, this concentrated radix are actually similar over here. Diameter, let me see. OK, we want the diameter of flatted butterfly, and we get the diameter of flatted butterfly, which is good. It's low diameter, low latency. This is one downside over there in the channel counts. This has too many channel counts, actually. But now we can actually have a small number of channel counts over here at reasonable channel widths. And as you can see over here, this is the interesting part. Our router outputs are actually not that many. So we can actually have a smaller, simpler router. But for that, you can read the paper for more detail. Let's take a look at the performance of this topology. So this work has evaluations with synthetic traffic as well as real workloads. You can see the synthetic traffic with different synthetic patterns and the real workloads. And one thing that we didn't really examine is routing strategies for different topologies. I think that's going to be very interesting to examine, but we didn't take a look at that. You can actually customize routing much better to different topologies. OK, so this is what we look like. It's a trade-off in the end. So it's no topology is going to be best at everything. This is the injection rate with uniform random. As you can see, meshes are actually pretty good over here with uniform random traffic. Flat and butterfly is somewhere over here. It doesn't do too well because it's really limiting. It's really partitioning the bandwidth across many channels, right? So it's as a result, in a bandwidth-limited scenario like uniform random, it's not doing too well. MEX is better than flat and butterfly, but it's very hard to reach the concentrated meshes over here. Actually, if you have MEX times 2, it's a little bit better over here. But it's very similar. OK. So this is uniform random with more nodes. With more nodes, we do better because meshes become very inefficient as you increase the number of nodes. So we're getting closer to mesh-like performance, and Flat and Butterfly is still not doing too well, as you can see. So as number of nodes scales, it's likely that MEX is going to get closer to the meshes over here. And Flat and Butterfly is not going to increase that much because as you increase the size of the network, Flat and Butterfly really partitions the network at a fine grain. As a result, you don't get much benefit from the diameter that's provided by the Flat and Butterfly. So the goal that we had with this work was actually to achieve scalability, and I think this graph shows that we're getting closer to scalability. So if you actually increase that to, I don't remember in the paper if we had 4,000 nodes or so, but for some reasons we may not have had it. Okay, so this is energy. If you look at energy, the energy story is actually not so bad also. This is 64 nodes, 256 nodes. It turns out Flat and Butterfly is actually quite good in terms of energy because it's not exercising these huge channels all the time. But MEX is also quite good, and meshes are actually pretty bad in terms of energy because you're really going through many, many routers. A high diameter actually is hurting you because you actually you're paying the routing overhead every time you go through a hop. That's the big downside with mesh type of topologies. With low diameter topologies, you're paying the routing overhead once, and then you're there. With meshes, you're paying a lot of overhead. You can see that the router energy is very, very high over here. And link energies are actually relatively similar because in the end, you may be driving a similar amount of interconnect or similar length of interconnect. So these are results with real workloads. So the results look good. So overall, MEX is, well, this is energy. In terms of energy, MEX is very similar to Flat and Butterfly, much better than meshes. And in terms of performance, MEX's performance is in terms of latency over here. MEX reduces latency significantly compared to Flat and Butterfly, and also meshes in this case. And this is the average packet latency over here on real workloads. Okay, so the summary. This is a new one-to-many topology that takes advantage of multi-drop express buses. It's good for planar substrates. It has very good connectivity and effective wire utilization. So there's more. The paper actually looks at other stuff like generalized express cubes that I mentioned. There's a framework and taxonomy for network on chip topologies. If you remember K-area N-cube models, K-area is the radix area. This is the radix of the router. And you can take a look at that in the paper. And I believe this is actually really interesting, useful for understanding, exploring on-chip interconnect options. In addition to proposing an interconnect, it provides a framework for understanding the interconnects as on-chip. And there's more to be done. We weren't very formal in this work. You can actually formalize a lot of what we've discussed in this work. But if you're interested in doing that, you can take a look at this paper. Okay, any questions? I covered relatively tough material very quickly. This actually, I don't think this is really easy material because there's a lot of theory that goes into this network design also, especially topology design. Don't worry, I won't ask this on the exam. Okay. So there are a bunch of other interconnect regions that I put over here. You can take a look at it yourself. So this is actually the latest one that I mentioned. So we actually want even lower diameter. If you can get diameter of 1, that's the ideal that you want. And this thing talks about, this uses actually some graph theory that I don't even understand, but Machi understands it really well, to actually design a network that is very low diameter. And if you're really interested, you can take a look at it. But you might want to read about graph theory before you go into this. So there's actually, this is one of the most scalable topologies, in my opinion, that is ever designed for on-chip networks today. In the future, who knows? But we'll see.
Say diameter of 1, you mean one hop from any
I mean, it's not always like that. So this actually has diameters of 2, but I think you can get diameter of 1 also. Ideally, you would like that, right?
like you have
Point to point. Ideally, you would like that, yes. I mean, we don't get that over here, but it's quite low over here. And I think the key question is how do you do it energy efficiently, of course, right? You can have a diameter 1, but you can be extremely energy inefficient. Okay, I'll leave it at that over here because that will open up a lot of can of worms. We actually discussed a bunch of things over here, but I'm not going to go through them. Okay, there are a lot of interesting other stuff in the bufferless network, but I'm not going to talk about that. So that brings us to the end of, I guess, all of the lectures. Any questions? I have the other set of slides, lecture 8. They're on the webpage, but they're not going to be covered on the exam. Don't worry about them if that's for your benefit. But Sahi, you had a question?
Yeah, you looked at all at interconnects that resemble wireless.
No, there is some work, but we haven't looked at it. On-chip wireless communication.
No, not actually wireless, but contention-based in the sense that, like in wireless, the set number of channels, buses, call them whatever you want, and you contend for a bus using one stream or another.
Yeah.
And when you have multiple ones, it's a flexible resource.
Mm-hmm.
It's obviously not the best when you have very heavy traffic.
Sure.
It
Mm-hmm.
can be very efficient if you don't have a lot.
Yeah. Yeah, I understand what you mean. We have not looked at it. I think that may be a good place to explore, actually. Any other questions? Yes. Optics. Yeah, I think that's very interesting. I think optics is already happening. On chip, I'm not sure. I think it's very interesting to explore. Researchers explore it. I'm not sure if we're still at the trade-off point where we want optics on chip, because there are conversion overheads also, right? If you can do optical computation, I think that would be very nice. But the conversion overheads are the most difficult part, in my opinion. But if you have very long links, for example, like fiber optic cables, I think those are good. And data centers, I think, I mentioned this yesterday, that's where the optics can actually help a lot as well. On chip, I'm not sure yet, but I think it's good to research. What else? You can ask about anything in the lecture so far. We've had 7 of them. So you know everything.
What about the last topic?
Last topic.
Topic of heterogeneous.
Well, we don't have time for it.
You have something to say about it?
Something to say about heterogeneous asymmetry? Well, I think it's a fundamental principle, so it's good. It was one of the fundamental principles, right? I think heterogeneity is important. And that last topic talks about like how to identify critical sections, bottlenecks, how to accelerate them, how to do that in a fine-grained manner. Very similar to when we covered parallel application memory scheduling briefly. I said you would like to prioritize those threads that actually cause contention for others at the semantic level, right? So I think that's a good topic. But it's going to take us at least 2 hours to cover it. What else? Yes, in the back.
At the beginning, we talked about DRAM memory, and you said latency was a problem in main memory. And now you talk about interconnect, and you put the memory even further away. It's not exact. I don't know if it's considered disaggregated memory, but what are the effects of that on the system?
Yeah. Well, if you're putting a lot of cores, I mean, we don't explicitly put the memory far away, right? You need. Yeah. So in this case, latency. The whole push for MEX, for example, it was to reduce latency. Mesh is terrible in terms of latency. You go from router to router to router to router. So that's why you need actually low diameter. That gets you to your memory much faster also. So if you have a diameter of 1, you're directly at the memory controller, right? Of course, you pay the interconnect latency somehow. So I don't know if that answers your question, but you need to design your interconnect also nicely such that it's low latency. And the MEX approach or the kilonok approach is really trying to get low latencies. And the slimnok approach that I didn't talk about, it's really to get low latencies so that you can communicate from point A to point B very quickly without a lot of overhead. So latency is still important, no question about that. Yes?
So all of the work that you've shown on interconnect does not discuss ordering and coherency.
Yeah.
Is there any work done on that, or is it only neglected it?
Yeah. You mean in bufferless deflection routing or in general?
In general,
Yeah.
the interconnect work that needs being done.
Yeah, there is certainly work on interconnects that try to preserve ordering. There is work. I can point you to them separately if you're interested. I think of coherency as some other substrate that you build on top of these things. If your interconnect preserves ordering, that's good. Like if ideally you have a bus, right? And bus enables you to see all of the requests, and it's a point of serialization, and you can order some things. But if that goes directly against scalability, right? So if you want ordering, maybe you want to build some other substrate on top of your interconnect. So bufferless actually gets rid of the ordering completely, right? Across packets or flits or whatever. But I think you can construct that ordering. But there is some work, for example, that looks at how do you create a virtual bus on top of a mesh-like substrate. There's a lot of overhead involved in that, in my opinion. So maybe I think I didn't talk about this because partially because it's a very, very hairy issue, I think, all of this coherence and ordering. And frankly, personally, I think we need to rethink that entire subsystem of coherence and ordering. I'm not sure if we really understand it also. Because when I read the papers, it's not really clear that the papers even understand it, those topics. So, but I think what you said is if you want some sort of ordering, and if you want your interconnect to preserve that ordering, you go back to imposing some order with some higher level structures, like a virtual bus on top of a very distributed network. And that naturally affects your scalability, I think. But I can point you to some works afterwards. What else? These are good questions. There are interactions, certainly, that we didn't examine. No more questions? We still have 11 minutes, so this is your chance to potentially figure out what's in the exam by asking the right questions. Okay. I'm not sure if that's the right question that I mentioned. Is that what we should talk about now? If there aren't any other questions. No questions?
Maybe while you discuss the exam,
Yeah, maybe. Okay, there's a question.
I think you mentioned probability more or less once, except yesterday, it wasn't here. It was something that you used it. The question is when you take things you talked about earlier this morning, like when you care about the arrival time of all the pieces in an application and scheduling. Another approach is to use error correction codes, erasure correction, basically create a few extra pieces so that you can send whenever enough around it. And then some are deflected, different routes, whatever, which you
Yeah.
know anyhow.
Yeah.
And that may allow you to, it complicates things to do too
Sure.
many of these. But then it allows you more flexibility, may not necessarily cost you higher latency.
Yeah. It causes more congestion, probably.
Yes, because you add load.
Yeah. Yeah, actually, I like that idea also. That's we haven't explored it, but that's one way of actually reducing latency. But it comes at the cost of energy, so it needs to be done very carefully. It comes at the cost of energy and congestion potentially.
The kind of thing that makes okay situations very good,
Yes,
but don't make terrible situations acceptable.
that's right. Yes, it can make terrible situations worse potentially if you don't do it right. Right. Yeah. But that's a very good point. I think those are some ideas. Those things are good for fault tolerance, also, right? It's really good for your latency, but also fault tolerance. Yeah. Yeah, that's an example of using redundancy for reducing latency and improving fault tolerance. Okay, what else? So now professors are asking questions so that students don't get to learn about the exam. That's fine. Students can ask questions too. But you asked a lot of questions. That's good so far. Okay, so let's talk about the exam very quickly, I think. I mean, I don't have a lot to say, actually. But it's going to be 2 hours, Monday, 10 to 12, right? It's not going to be hard, I think. So don't worry about it. But I think know the material. So I'm going to focus on more fundamental things, especially things that we've spent time in class are the things that you should probably expect questions on. Not the nitty-gritty on some slide that we didn't really touch upon. That's not interesting. Things that we've spent some time on class, things that are emphasized, fundamentals, those are the most important things, clearly, right? The readings that are assigned, those are important. So you can get positive points from them, of course, separately from the exam, but I think those readings are a little bit higher priority, as we discussed, so you might want to know them for the exam. That's good. I know, it's going to be multiple choice. Probably, we haven't decided the exact number of questions yet, but expect at most 50 questions or so. 50. 2 hours. 120 divided by 50 is 2.4, right?
2 minutes per okay.
Exactly. Yeah, so it's not, it's at most, basically.
Can
Yeah.
you give a couple of examples that people will get the spirit? I think that's, from what I heard, people do not get any idea of what a kind of, I mean, not, it can be in,
Okay.
as you say, out of 50, it can be even,
Well, I think it could be.
no,
You want me to make up questions on the fly?
yeah, it's people will get like what you have in mind. I think
Yeah.
That can help.
Make up one question, an example of what kind of.
I see. Do you have any thoughts on that?
I have the thoughts, yeah.
Out of 50, you need to.
First of all, I'll start, before giving an example, I'll start by saying what not going to be in there, okay? You don't have to remember any initials, you don't have to remember numbers, okay?
Well, DRAM may be a good one. Dynamic random access memory, for example.
Yeah, you need to remember what's DRAM, but not what's PowerBS, for example.
Yeah, exactly. That's
If you
it.
need to remember some initials or a name, we remind you. We remind you what the name stands for, what it means, what it does even. An example is, we've seen a technique that does A. Technique A helps to solve problem X. What are additional techniques that can solve problem X? This is for example, and the additional techniques, of course, we've seen them.
Or it could be asking the key idea of that technique, for example. We've seen this technique. What is the key idea? Something like that.
So this is the direction. No, nothing that this we have seen technique A. What does technique A do? And exactly remember. No, you have like more. We help you with some background, with some reminders of what we've seen, and the concepts, the fundamentals. If you know them, then you'll be able to answer the question. Anything else you want to mention?
No, I think that's all. Any questions that you may have?
And by the way, if you're not sure about the exam, let's say you missed a few questions, you have the review assignments that can help you substantially increase the grade. So up to you. Anything else?
The exam is going to be here?
Yeah.
Not in this class. I think it's published. It's going to be. If not, I'll publish. I'll check. I'll make sure to publish. You know what? I'll make sure to publish it, even if it's published in the syllabus. Okay. Thank you. Anything else? I'm going to be in the exam. Although I'm not sure Arnold's going to be in the exam, but I'm going to enter the exam. Of course, if you have any questions, it will be multiple choice. So we'll see. Probably it will be a computerized form, something like that. And that's it.
Yeah, it should be fun.
And no additional auxiliary material that you bring with you. Just bring yourself and a pen. That's it.
And a good mind so that you can think clearly.
Yeah. No need for a calculator.
That's right. Yeah. We won't. I mean, if there is any calculation, it'll be very simple calculation. You should be able to do that very easily. If there is any calculation.
Okay. Oh no, thanks a lot.
Okay. Well, thank you.
everybody enjoyed the course, from the undergrads to the PhDs and professors, and I hope to see you again here.
Okay, I hope
Not
so.
only one time. I hope you will forget or stop counting how many times you come to Israel.
Yeah, we'll need to work on that a little bit more. Then, but yeah, I enjoyed it also. It was great to be here. It's great that people were so interactive. And if you have questions, feel free to email me. I'll be around until Monday afternoon. And after that, I'll be gone.
But email still works.
What?
But
Email still works, yes. But if you want to get a hold of me before that, then you can still get a hold of me around here. I'll be at Technion actually on Sunday and Monday also. But you can always get a hold of me over email if you have any questions then. I enjoyed it quite a bit also, the interactions. I'd be happy to come back.
We'll be happy to see new stuff.
New stuff.
Yeah.
Yeah, I'm sure there will be new stuff.
Or forget the current stuff quickly so you can use it.
I see. That's a good idea. Okay.
That's
Well,
it. Thank you.
yeah, thanks for coming.